Good evening, mathematicians and lay math enthusiasts, and everyone else. Welcome. My name is Jeff Cook, and this is the 7th video on a series on a direct proof of the Riemann hypothesis. If this is the first time you have come to hear about this, I would encourage you to watch over the previous 6 videos. So you'll hear in the first couple videos, I didn't have a mic or a mixing board, and it sounds really poor quality, but I decided I did get some more interest than expected with this. So I went and bought a nice mic and got a little better audio. So, but it's listenable. You're just gonna have to get caught up, I guess, if you're new. I'm assuming most of the people that are landing here have watched some of the other videos, because I have some subscribers that have gained interest, and we do have thousands of reads. I haven't checked in a while of the paper itself. It's paper in preprint, and it's by myself and Greg Volk and Dennis Allen. Okay, so you can watch the other videos on who we all are. All right, this video is going to be very interesting, I think. I did say in the last video, I'm going to save the 7th to be the last in this series. And I was going to reserve it for if somebody found an error, or if somebody defended the work. All right, after the last one, there has been some discussion on the final statement of the paper. Okay, so no one has found any problems anywhere through the paper. They find a problem with the last statement, and this is going to discuss that. And it's kind of given me some. It's been a year. I think a year since either I uploaded the video or I started this video. It's been a year. I think it was September of last year. Started putting these videos up. I think it's time to go ahead and make another one. And this is the reason is because the issue is coming up, and it's based on a misunderstanding of the mathematics involved. And it's from some accomplished mathematicians, so I do take that seriously. And so, as I discussed, if you look at the paper, if you kind of go download it here, you can. I don't know where it's ranking these days. I just kind of use this image. So this was it? Is there data on here? No. From a video a long time ago, the ranking was higher, I think, because it's been up for a year or so. The ranking is a little lower, but you can find it at ResearchGate, and you can do a search there for it and find it a variety of different ways. Okay, here's the publication number and all that. Okay, so. The issue, I'm going to get into it, and I'm going to show that it brings up something something that involves the law of non-contradiction. So this is, for me, a really annoying part of logic. Okay, the law of non-contradiction is not the annoying part. The fact that some people still fail to grasp it, and particularly in terms of arguments on theology and things like that, they misunderstand it. All right, in mathematics, it's very well defined. All right, some may say it's not a law; it's a principle. Okay, the reason is because it's not been proven. It's one of those things that is self-evident. All right, and so that's what a lot of people have a problem with. So, what is exactly self-evident? All right, so this law of non-contradiction goes way back in logic. And it often comes up in the fallacy, the logical fallacy, that you cannot prove a negative. All right, there was a magician, I don't remember his name, I don't know if he's still alive, John Randy or something like that, something Randy, and he would brag that he was he self-identified himself as a skeptic, okay, skeptic of telepathy and everything, okay, so all humans should be skeptical anyway, so that's kind of like saying, hey, I identify myself as a human. Well, how proud you must be. Okay, we all should be skeptical. All right. So, but he would state outright, flat outright, based on this Middle Ages logical fallacy, that you cannot prove a negative. Well, you can prove a negative, and mathematicians do it all the time. For instance, I can prove that there are no even primes greater than 2. Okay, so this is proving a negative is done very easily. Now, some things are difficult to prove the negative, but that doesn't mean you can't prove it. All right, so this issue comes up in this paper, in this proof at the very end, because what are we doing? We're proving that there are no non-critical, non-trivial zeros of the zeta function. So that's proving the negative. But like I said, it's not that hard, but there are some that really have a hard time grasping things that are self-evident. It's true. I mean, because it may not be evident to yourself. All right, but we're going to go through, and I'm throwing an analogy to that you're going to really understand it. And the best part about this is that mathematicians should get this, but lay mathematicians and even non-mathematicians are easily going to get this. Okay, it's very straightforward, and it takes a little bit of physical juggling around some things with physics. Okay, so I'll explain better as we get going. All right, so the law of non-contradiction. Well, what is the law of non-contradiction? It's saying that two opposing statements cannot both be true at the same time within the same respect. All right, so I cannot say I exist and I don't exist at the same time in the same respect. And what does in the same respect mean? Say why I exist as a human and I don't exist as a human at the same time. Does that make sense? This is considered self-evident. Now, there are some people that have proven it. I've seen some proofs on it, but there's no reason to do it. So, because it's self-evident. All right. Now, I understand that this term has been used in the United States here in our Declaration of Independence, right? So, and some may say, well, we don't hold these truths to be self-evident. It doesn't mean that self-evidence is wrong. It just means we don't hold that as self-evident. Okay. But the law of non-contradiction is self-evident, and it could be proven. All right. Just no one's ever really seen the need. In math, though, it is assumed. Okay, almost all proofs in contradiction involve this. Okay, so if it equals 2 and it equals 1, then it's obviously not true. All right, so that's that would be using that. Got it? All right, we're going to discuss this and how it applies because we are proving the negative, and by doing certain things, you're going to come across this issue. And there's a couple mathematicians that brought it up. One in the YouTube comments of the last video, and a mathematician we've been emailing back and forth. And I don't know about the one on YouTube, but definitely the other is an accomplished mathematician. And it could be the same guy. It could be because it came out like the same day or something. So, I think we did provide these YouTube videos to him. So I think he does watch these. Hope you do, because I hope you get this. All right, you will actually. You will. All right, but let's start way at the beginning. How do we test a proof? I know a lot about testing. I used to do it for a living. I was actually sought after. I worked for some very big companies, and any companies we partnered with also wanted me to come work for them. I was very good at testing and proof, all right, at testing anything. I would even test grammar, all right? So there was a lot of testing computer software, all right? And I did it most time black box. I can code in some languages, but that's not my forte. I like black box. Now, it is Greg that brought up the analogy. I had never heard that proofs can be thought of this way as well. But, you know, he's taught it in school, and this is at the university, and this is, it makes sense. So I'm gonna show you here. We're gonna start very beginning. How do you test a proof? All right, this is gonna be going back to the basics. So really high thinking individuals who don't want to believe something are gonna forget some of the basic premises of logic that they really need to be following, because if you really don't want the proof to be valid, then you're going to stretch your understanding of logic to the limits, right? As you should. All right. So, and I'd say you shouldn't want a proof to be, right. You shouldn't want it to be wrong. You should just want it to be checked, want it to be tested. How do we do that? All right, so this is a black box I did up, a little 3D modeling here. All right, simple proof, one box, one door, okay? You open the proof up, you get some controls, you perform some operations, and you open the back door. Now, if you have a proof with 3 lemmas, oh boy. Yeah, I can see the comments now. Just go on, have fun. All right, anyway, here we go. 3 boxes, 3 black boxes, all connected. Each one has a door, and then after you go through one, and then the next, and then the next. All right, so lemma 1, lemma 2, lemma 3. The paper has 3 lemmas, and these are small proofs that lead to a bigger. You're doing a step-by-step operation. All right, so you perform some operations, perform some manipulations, some controls, and the next door opens, and then you go here to this box, and you go and you manipulate that, and then the third, and you do that, and if you get everything right, then the back door opens, and you get your proof. Okay, that is how we're going to test it. You cannot see what's inside of it. All right, you cannot skip ahead to see the end result. You have to go through lemma 1 and then through lemma 2 and lemma 3. All right, if you think you can eliminate certain lemmas based on some, well, it's just a pointless lemma. Okay, fine, show it. I'm going to show here why not one of these is something you could skip over, and you will understand and agree afterwards, okay, if you are following some basic logic. But why cover this basic matter? Well, kind of said, this is, we get these comments. And, I know not everyone is ever going to always, agree with the proof, all right? That's fine. It doesn't matter if you do or not. But I did say in other videos, and I believe it completely, that proof is only as good as the individual you're trying to prove it to accepts it. If you're in a court of law, I don't care if it's true or not. If the jury doesn't believe it, then you're in trouble, right? So that is the case. What is proof? You're proving it to yourself, or are you proving it to somebody else? And this is not the way this is taught in schools. This is not the way people typically think of it. But in the end, that is the way it works, which is why I love patents and inventions and creations, and exactly why I put the zeta function in this form that we're going to discuss, because you're creating something and it works. And you can deny it all you want. It's right in front of your face. I like it with physical inventions. You build something and it's working. It's supposed to do this and it does that, and I don't need to prove anything. It's self-evident, right? It's going. It's doing what it says. And that's why this paper was set up this way. So the arguments are going to be very difficult. Errors could be found, but no errors have been found. Every single equation from start to finish is been, agreed. Yeah, that's right. But the last final statements are in question, and I will show you why that is an issue. Here is the issue. Two different quotes, likely two different people. All right. You appear to be using, you being I and my authors, you appear to be using the functional equation only to motivate your definition 2, not as a logical step in the proof. So one could apply Occam's razor and just start the proof of lemma 1 with define, and then continue on with 2. And we're going to go over that. All right, so what is Occam's razor? Anyone that's seen the movie Contact, this principle has been misquoted a lot ever since the movie. Now, I understand why they do it in the movie, because you could try to communicate to a wider audience, got to keep it simple, stupid, right, type of thing. So the statement of Occam's razor, what it is, or the principle of parsimony, is this, that do not multiply entities beyond necessity. All right, if you're setting up an experiment, you want to keep the number of assumptions low. All right, you never prove any one thing with an experiment. You just support your hypothesis. So those with fewer assumptions and more controls is a better supports the hypothesis. Okay, that's Occam's razor. What it does not state is what was stated in the movie Contact, which is, given all things being equal, the simpler of the two tends to be the true. All right, that is not the case. In fact, many times the simpler is false. Okay, it is simply not what Occam's razor states. It is honestly, it's misrepresented. It served its purpose in the movie, and I like the movie quite a lot. It's just, we're talking really, what is Occam's razor? And what he's saying is basically, if we don't need these lemmas, then they take them out. And I agree with that, all right? So if we don't need them, all right? And then the other one is lemmas 1, 2, 3 have nothing to do with the properties of the zeta function. That's exactly what he's saying here. You appear to be using the functional equation only to motivate your definition, all right? So have nothing to do with the properties of the zeta function, all right? It is possible to replace, therefore, zeta of s everywhere by any number z with no relation to s. That is not true, all right? The equation, the zeta function was put in the form of the driven harmonic oscillator. The moment it is done, the moment it is in that form, it shares all the mathematical properties of a driven harmonic oscillator. Okay, the moment it is shown to be derived, you can derive that oscillator form, then it shares all the properties. Okay, nothing to do with the functional equation anymore. It has now to do more with driven harmonic oscillator. Okay, so but let's get into it. So this is what the arguments have been. All right, yeah, because if you do this, this is what happens. All right, so what are we speaking of? This is what happened. Counter argument is this, all right? One can swap out the zeta function with f of s. F of s is the beginning of the paper. And skip the lemmas altogether, all right? F of s, here it is, a couple different forms. It's a Selberg-Euler product, very simple one I created just for sake of argument. All right, has some critical zeros, those on the critical line, some non-critical off the critical line, and one trivial zero. So -2 would make f of s go to 0. Okay, so we use it to discuss, and with Selberg-Euler products, if you haven't seen the other videos, if you can apply a Selberg-Euler product that has non-critical zeros to the proof, and it works also, then it shows that the proof is wrong. Okay, so basically, I'm in the paper, I'm a qualification discuss. We're going to put one in there, and we're going to show you can't apply it to this proof. And so what these individuals done is they just skipped all the lemmas that doesn't work and go straight to the very end, the final conclusion. We're going to show what the consequences of that are. Okay, so what are the lemmas in the paper? All right. To refresh your memory, or if you're new, here they are. Lemma 1 is that there exists upsilon of s, a function that satisfies this equation, okay? All right, so this is an oscillator form, and I'm going to expand it out and show you what A of s is and all this. We're going to go over that, all right? So there it is now in oscillator form, all right? So it now has all the properties of driven harmonic oscillator. Yes, we're going to get into that, okay? So if lemma could be skipped, then the Riemann oscillator is eliminated. All right, if the Riemann oscillator is eliminated, then the representation of the zeta function is not a system or machine, and you can disregard all of its functionality. All right, and you can also disregard that its input s. So upsilon of s, that's dependent on s. But if you skip all that, skip lemma 1, then yeah, we could do that, right? Possibly. All right, if the above could be done, then one could solve for the zeros either in terms of upsilon or of s. That would be cool. Because then we could disprove it. Because there is a solution in terms of upsilon. We'll get into that. Is it a solution or extraneous? We'll get into that. All right. But since solving for s has no solutions, and no mathematicians are arguing that, all right, s has no solutions from the final result of the paper. And if you don't know what that means, it means that there are no type 2 zeros, which means that there are no non-trivial zeros off the critical line. Okay, so it's a really important part. It's the very end of the paper. All right. So the empty image solution in terms of upsilon would refute the proof. Right? If we could get rid of all those lemmas, then yeah, we could refute the proof. All right. It's the solution in terms of upsilon without having a solution in terms of upsilon. Input suggests that all arguments are possible. Well, asking the real part, he says no solutions are possible because I don't have a part in this. Okay? See where this goes? All right. Is this logical? Can we skip the lemmas? Well, let's continue on. What are the rest of the lemmas? Let's lemma 2. All right. Only one term of the zeta function in the form of 3, which is the oscillator form, has zeros. Okay. So if we didn't prove this, oops, where'd it go? Hold on. Bumped something. Yeah. If we can't prove this, then it means that one of these terms could be equal to 0. If it could be a 0, then there's more than just 2 types of zeros. If there's more than 2 types of zeros, then that final result could be argued. There could be a counterexample. There could be 50 types of solutions, and one of those could be a counterargument to the solution that is being argued with the logic here of the counterargument. Okay, so for instance, these gentlemen's point here is dependent on there only being 2 types of solutions. All right, we have to prove there was only 2 types of solutions. Okay, otherwise I could find type 50 that could be a counterexample to the type 2 solution. We're only dealing with the type 2 solution. You have to prove that actually that there are only 2 types first. If there's 3 types, type 3 might disprove type 2. So it doesn't really matter. Okay, then we can kind of go into the law of non-contradiction, but we're not there yet, okay, because we have to have lemma 2. It's super simple. If you have lemma 1, it's very easy, okay? So no reason to do that. All right, but if lemma 2 could be skipped, then the possibility of one of the terms in the Riemann oscillator could be equal to 0, and the possibility of any results of lemma 3 would be in question. So what is lemma 3? That the Riemann zeta function has 2 types. Okay? Now we're going to break this down. What are some of the definitions? How do we define this type? Zeta equals 0 and upsilon equals 0 if and only if real part equals 1/2. That's type 1. Type 2 is zeta function equals 0 and upsilon equals 0, does not equal 0 if and only if real part does not equal 1/2. So both upsilon and the real part are reverse implied. You need both of them to have some solution to have any meaning. By definition, This is the definition. And that's why the mathematician said, something about it. But we really need to know upsilon and real part, and we're going to actually get into that. All right, if lemma 3 can be skipped, as we talked about before, there could be more than just 2 types of zeros of the zeta function. All right, so what's going on is this. They took an f of s, or a Selberg-Euler product. They opened the door. They tried to get it through lemma 1. Didn't work. Not very easy. Maybe it would work, but it's really difficult. It's as difficult as finding an L function for a Selberg-Euler product. Why didn't anyone find an L function for any Selberg-Euler products? Because you have to derive them. You have to actually show that one follows the other. No one's been able to do that, and it may not be possible. All right. In the same way, you have to take the function equation and derive the oscillator form. You can't just say, hey, this is the L function for the Selberg-Euler product. No, you have to go and derive it. And you can't just say, hey, this is the Riemann oscillator. No, you have to derive it. Okay, so what they have done is they've taken off the first door, looked at it, go, that doesn't work. That's not easy. I'm skipping that. And I'm going to go to this back door, and I'm going to come up with an empty image, because that's what results. And I discussed a little bit about empty images. I think it's made one comment on it, and it's not something everyone knows. But empty image is basically the input you give. You put some empty input in there, because you can't put any real part in. Therefore, you're not going to get anything real out. All right. If you have no real part in, you're not going to get anything out. It's an empty image. And you can go read a image of a function, Wikipedia, empty image, some of these meanings elsewhere. All right. Maybe I'll do a video of it someday. Probably not, though. But does this make any sense? What is an empty image? All right. Well, let's look at it in terms of an oscillator. What is an oscillator? All right. More specifically, what is a driven harmonic oscillator? All right. So I think the problem is not the mathematicians. It's not. I am taking full responsibility. Me, I took liberties of certain things. Not saying my co-authors disagreed or not, but I think Greg, he really wanted to keep the discussion in there on the driven harmonic oscillators. All right. We took it all out to keep it pure number theory or purely mathematics. All right. But I think that's a mistake. And I think we need to go rethink that. And we're talking about it. I know because Jonathan Sandau, if you've heard the other videos, I was a big fan of him, and he was working a bit on this. I presented the proof to him like I did with Greg and Denny, and he's saying you really need to have some discussion on oscillators, because mathematicians, it may have been a long time since they studied it, or may have never studied it at all. Give them the background on it. Don't leave anything for their assumption, because that's where the problem is I assumed that you would understand by looking at the equation that you, the reader, would say that has all these other mathematical properties too. But no, that's not fair. It really should be, the oscillator should be in there. And Greg said that's the gold right there. The oscillator is the beauty of this paper and this proof. The fact that it's a machine, you have given the zeta function these properties, you've created it, and we went and hammered things out from there. Okay, all of it's been removed, we discussed it, and that's why I'm making this video. We're going to put it back in. We're just going to put some discussion and then talk about harmonic oscillators. Okay, I'm going to discuss it now so people get up to speed on the videos now, because time is always limited. All right, good. All right. So what is an oscillator? Now, most people would give like an analogy of a swing. A swing going back and forth. It's got some friction. It's got two opposing forces, one forward, one backward. And if you have somebody pushing the swing externally, that would be a driven harmonic oscillator. So as the external force as well. That may be in sync in frequency with the others. If you really want to keep going, it's in sync. All right. One of the other interesting properties of a driven harmonic oscillator is the resonance, the frequency. It cannot exist beyond a certain argument. All right, so we're in the critical strip, so it's always good for this paper, so I didn't discuss any of that. But yeah, there are certain properties of oscillators, and they're mathematical restrictions that have to be taken into consideration. It's really neat. The world operates off that, and it's described mathematically, and mathematics is solid. That's why this was created like this. All right, good. But here I'm going to talk about, for sake of analogy, to discuss the whole law of non-contradiction. I'm going to use an external combustion engine, which is an oscillator of a sort, and particularly this one. All right. So the external force would be this fire or this heat All right, so let's look gas in, and it's oscillator, but the external force is here. It's going to push something back up, and you're going to actually, it's going to keep repeating. Okay, so it's called an external combustion engine. All right, and there were a lot of machines that were built in this way in the early days. Okay, so actually it was pretty useful. All right, but it's not like your typical oscillator, but it is. All right, so it's I mean, like a swing is a simpler way, but we're going to use this analogy because it has the gas. Okay, and we're going to do it. All right, mathematically, this is what it looks like. Okay, so here you have derivatives of c. So if c is position, get a little physics background here. C is position. What's the derivative of position? Of the functional equation of its position? Well, it's velocity. What's the derivative of velocity? It's acceleration. Okay, so what is omega naught? Well, this is the undamped frequency. Okay, so you have no damping, nothing slowing it down. The damping, we'll get into that in a second. All right, it's you could call it the fundamental frequency. Okay, all right, what is upsilon? It's in the paper. It's all about this proof. Upsilon is the damping ratio. Physically, it is dimensionless. Okay, so if we're talking about force, if F is force, T is time, M is mass, this is dimensionless. It's a ratio. Okay, and we're gonna get into what I don't think I state exactly in this what it's a ratio of, but we're gonna show some relationships with it to give a little better understanding what upsilon is, what you can do with it, what you cannot do with it. First thing you want to understand is that the oscillator, it has two forces in opposite directions. Remember, the swing is going back, one pulling that way, one pulling this way, not including yet the external force. All right, so this is how they're defined. Okay, or I don't know if that apostrophe is there. Yeah, it must be a derivative of c or a typo. I don't remember. I'm looking at it. Somehow it looks funny for me all of a sudden. Anyway, somebody can check that for me, or I'll check later. All right. So good. Now, there are many types of oscillators. All right, you could have, instead of force, you can have electrical potential, voltage. All right, and there's many different ways to do it. There's all sorts of oscillators in the world. All are mathematically identical, and all are mathematically identical to the Riemann zeta function. That's proven in the paper. All right, the two constant factors in F1 and F2 are, we got K, which is the spring constant. Let me get my cursor. Spring constant and damping coefficient. Okay, so you see it then has a damping ratio in there. There's probably some other ways to express it as well. All right, good. All right, what is K? It's a spring constant. It's a force. Okay. All right, good. All right. Now, what happens if we tune this oscillator? We know the mass of the object we're lifting, and we can adjust the spring, okay, so that K, the numerical value of K is equal to M. Well then, and this is what I did to set up the paper so that it's simplified. It just eliminates the fundamental frequency in the second term. You still have it squared here, but it is gone. It just reduces to 1, okay, when you do that. And then you get what you got in paper, a quadratic. It's pretty neat. Okay, good. See, because the two there has to end up give you a quadratic solution. All right, good. All right, now let's look at it. So we got derivatives. Yeah, I think that's good. That's pretty clear. Now, the Riemann oscillator. Remember, I said I like things when they work or they don't work. There's the proof. It's self-evident. Okay, this is a functioning Riemann oscillator. All right, it's a functioning oscillator. It does something. You take t and you can give any value of t. S is constant, right? You apply your argument, your fuel, and then you t any value, and it's going to give you a point somewhere, and you can map that. Okay. Now this is not equal to the zeta function at any t except t equals 0. Now you remember the derivatives. That's taken at infinitesimal t, very small t. All right. So we're getting closer to how where this leads to the zeta function. If you would take t to 0, this would be equal to the Dirichlet eta function, or as Jonathan Sundow calls it, the alternating zeta function, and the relationship between that and the zeta function is this constant here, which is analogous to mass, or m. Okay, good. This then is fundamental frequency, and so on and so forth. All right, good. Important things to note: upsilon is independent of t, but is a function of s. You take away s, upsilon has no meaning. All right, no meaning at all. All right, the undamped frequency is also independent of t and a function of s. All right, each of the functional equations in the terms are derivatives. Okay, just like a Riemann oscillator. So if you take this functional equation, you're going to end up with the term that would be right here as a result. And if you take this one, you're you're going to end up with a term that will end up here at t equals 0. And if you note, the function that is summed that gives the Riemann zeta function, if you integrate it, you would get this function, which is the analytic continuation of a geometric series. All of them are, okay? And if it is one's derivative, you integrate the previous, then you get the next one over, okay? So this would go into this term. That's how that works, okay? So here's what it looks like at t equals 0. It equals the zeta function. All right, how is upsilon defined? Well, you can define it in a variety of different ways, all right? So it is independent of the zeta function. Here is, you give it any argument s, and you're going to get a value. All right. But how is it derived in the paper? Well, it's derived in lemma 1. All right. So you're going through and you're starting, and we're doing it with more of a trigonometric and manipulations. But they're not trigonometric. They're algebraic. They're algebra. Okay. But we are manipulating it, and we're getting upsilon out of it from the functional equation. This is functional equation not in here, but it starts getting big, and we then, within lemma 1, we get upsilon. We didn't just define it, we derived it. Just like if you have an L function, you're going to have to manipulate the other to show that L function is actually possible for a Selberg-Euler product. In this way, too, you have to prove that the oscillator form, or upsilon involved in it, is possible for Selberg-Euler product. It is possible for the Riemann zeta function. We did it. All right, let's drive it home with this. All right, I'd like to drive anything home with this, okay? So this is, I think, is the world's fastest car. I don't know how old this picture is. Maybe it's not anymore. And the question we're going to ask is, what type of gas does this take? Okay? We're going to say it takes type 1 or type 2 gas. All right? Type 1 gas is going to have this proprietary formula. You see where I'm going with this? It's got this formula. We were asking, does it take type 1 or type 2 gas? Type 1 gas has upsilon equals 0 and real part of s equal to 1/2. All right? Has to have both of them. Otherwise, it's not by the proprietary formula. It's not the same gas. All right? Now, type 2 is upsilon not equal to 0 and real part of s not equal to 1/2. Do you see where I'm going with this? This is set up so that anyone can understand it. All right? What part of the definition of the type does one eliminate if s is disregarded, as those comments were given? All right? We disregard s. What's going to disappear? All right? The real part. And the real part has no solution. We already know that no one's questioning it. The real part has no solution in the type 2 0. Okay, it does for the type 1. Those are all the critical zeros, right? But type 2, we know that if you try to rearrange solve, it's basic algebra is going to show now you can't get any real part arguments out of type 2. So the question is, oh, well, we got upsilon not equal to 0, and we have a solution for that. Yeah, I know, but by definition, we need the real part of s not equal to 1/2. That has to be shown too. That's not a solution. This is not a solution. This is a solution that's been given as a counterargument. Is when upsilon of s is equal to minus upsilon of 1 minus the complex conjugate of s. All right, then it's a solution for all arguments s. Well, no, we just try to solve for any argument s, and it shows there's no real done with the real part. They're all imaginary, and there's only one. So that's a little bit of a problem. That's not a solution, and let's discuss that a little bit more. Why? All right. When there's no s, not a solution. S is the input to the function. All right. Now let's just forget the types. It's just say it is the gas, or the component we're looking for in the gas. All right. If I provide schematics to build a car, this car, and this car, we're going to call it Zeta. This car involves an input S in terms of 2 types of fuel. We don't know which one. We know it takes 1 type, real part 1/2. All right. But we also have an electrical damping functionality. I'm giving you instructions on how to build the proof. I'm giving you instructions on how to build this car. All right. It has some electrical damping functionality in there, and it gives this ratio upsilon. All right. And the battery is recharged when the engine's running. All right. Upsilon. And so therefore, upsilon is dependent on S. All right. And you skip the steps to build the fuel line. You have not built this. You have built this, a Tesla. You see? You're not building a combustion engine anymore. You're building an electric car. Just because the electric system is running, if your function f of s is running still, that's fine. It's just an electric car. It's just a different thing. It's not equivalent to the zeta function. The zeta function is analogous here. It's something that depends on s. S, the real part of s, And let's say the engine running is analogous to the zeta function going to 0. All right, there's 0 problems. Let's just say. All right, you're gonna have some problem if it's not 0. I don't know, it's just a way to say it. All right, good. So if you skip the steps, you're not building the same proof. All right, it's not, because they're all required, and you end up with a different result. All right, the question the proof asks is, does zeta of s equal 0? Does it run on type 2 fuel within the critical strip? We're asking in terms of the real part, and the real part answer is no, it doesn't. It can't. If you ask upsilon, it's like, yeah, everything's working right. All solutions are possible. And you ask the real part, it's like, no solutions are possible. That's the law of non-contradiction. And who are we asking? Who do we care? Do we care about upsilon? His electrical system's running fine. It's fine. No, I'm functioning fine. If you have a computer asking, it's like, no, we're good. But you find out, you ask real parts, we got a problem here. We got no fuel line. We can't drive without the fuel line. Do you understand this? I think you do. Type 2 fuel, by definition, in its proprietary formula, includes the real part of S not equal to 1/2. If you can't get a real part, any solution's real part to work, then we have a problem. All right. While upsilon of S is equal to minus upsilon of 1 minus complex conjugate of S, is part of the solution of the engine functioning properly. It is only the damping component. The damping system may still be intact with type 2 fuel, but the engine has no real solution. There must be a solution in terms of the real part, else we have a problem. Because by definition, we need both upsilon and real part. By the law of non-contradiction, a combustion engine cannot both require gasoline and not require gasoline at the same time in the same respect. Nor can one reasonably state that upsilon of S equals minus upsilon of 1 minus complex conjugate of S is possible for every type 2 0, while at the same time, no real part of S is possible in the same respect. Upsilon of S equal to minus upsilon of 1 minus complex conjugate of S is dependent on S, and therefore having no real part of S, S therefore must be imaginary, which is actually the way you derive it. You get an imaginary solution. But a real number cannot be both real and imaginary at the same time in the same respect. Not to mention the lack of a symmetry that would cause and the whole Riemann symmetric vertice property. Do you understand this? Does this make sense? By definition, which wanted to be skipped. You wanted to skip all, not you, but certain people wanted to skip these lemmas, and and end up with saying there are 2 parts. The lemmas prove that there are 2 types. That there are only 2 types, and by definition, you need to have upsilon and the real part. This it shares all the mathematics of a driven harmonic oscillator. It's the moment it was put in that form, the Riemann zeta function now shares all of those properties. It can be shown. You can't eliminate them at will. It's like, well, I don't like his arms, so I'm just going to take them off. No, you don't get to manipulate it that way. Sorry, you don't. But moving forward, if you have stayed at the end of this, I have something really, really interesting to share. I would say it is my greatest idea to date. And if this is anything like all of any other ideas I thought was great, most people are going to hate it. All right. So it's the ideas that I think are silly, people really, really like, and the ideas that I really love, people hate. But this one, I want you to think about this. Moving forward, though, I'm going to make some updates on the proof, okay? Before we get to my great idea. And I'm going to include some discussion on the oscillator that the proof presents. But I'm going to start moving away from proof for a while to something more important and what people are calling hot, okay? All right? Something going on in the world right now is pretty neat, all right? The reason I'm doing this is because, well, proof is not a win-win game. If you are working on the Riemann hypothesis right now, and then you're competing, and you're not going to be happy if I win it. If your proof gets accepted over anyone else's, they're not going to be happy with it. All right, I'm different. I don't care. All right, so I hope it's wrong, because then I get to work on it some more. But either way, what I've seen, people are unhappy. It's just not fun, you know. I mean, let's face it. You know, if the game's over and nobody's happy with you, then that's just not fun. I don't want to do that. It's just not interesting. And so, I am going to move past it to something that is a win-win game, and I think you're really gonna like it. So, mathematicians, lay math enthusiasts, and investors, and you might want to pay attention. The next video is about ready to air after this. All right, so if you're watching the recorded version, you can go find it. But if you're watching the premiere, stay on and listen. It's premiering immediately after this on this idea, and I want you to hear it out, all right? NFTs are a win-win game. All right, listen to this. Just hear me out. I know it's going to sound crazy. I spoke with all my mathematicians. I spoke with friends who are not mathematicians, those trading in NFTs, and all are going, okay, that's kind of cool. That's kind of a really good idea. And it's never been done. All right? Think about selling, well, let's just think about mathematical objects. What is a mathematical object? A proof is a mathematical object. An equation is a mathematical object. E equals mc squared. Euler's identity. Okay, all of these are mathematical objects. So too is Euclid's long division. I think it's Euclid, wasn't it? Long division. That's a very valuable algorithm that has been used for centuries, right? And about, 10 so years ago, U.S. patent offices stopped allowing algorithms to be patented, saying that they're a product of nature. All right? Well, my thought is, how would it be a product of nature if I created it? Think about it. If I created the Riemann oscillator, you see where I'm going with this? Not entirely. You don't know exactly where it's going. If I created it, then how is it a product of nature? And let's draw the analogy to patenting drugs. Okay, you got the molecule. Who's to say that that molecule doesn't exist somewhere in nature? Most of the time it does. Yet they still get a patent. Algorithms can't. Algorithms and math have been devalued to nothing. And my idea is to change that. Why not? If I give you a painting for free and say, hey, go, you like a painting? Yeah, that's good. All right, take it. You're probably going to put it in the closet, put it in the garage, or so on and so forth. All right? And anytime I come over, you're going to quick put it on the wall, if you can remember. All right. If you buy that, even for $50, that's going to have more value to you. All right? So let me give you a better example. So when I was a teenager, there was this Christian rock band, and their music wasn't in-your-face Christian, which most teenagers wouldn't get into, at least not my friends in that. But it was cool music, and the people, some interview asked them, said, well, if you're Christians, why are you selling your music? Why don't you just give it to the world for free? It's a really dumb question. Then they said, well, we used to. We used to give away our tapes after the concerts, and no one took them. You see? There was no value placed on them. No one listened to them. They enjoyed the concert, didn't take the tapes. The moment the moment we started selling them, everyone wanted them, and our career took off. And they probably, I don't know, if they're still around or anything like that. I don't. The name's band is Petra, and yeah. So think about this, because they placed value on that. They placed value on that. They said, we say that this is worth $5 or $10 for this tape, and you're going, I agree, that's worth $5, $10. I'm gonna take that. All right. If I give you your art for free, you're gonna put it in the garage. If you buy it for $300, you might see it as value. You might trade it. You might sell it. You might make a little money off it too. So I made a little money off of selling it to you, and you make a little money off of it, and it goes on and on and on. That's a win-win game. And why not do that with math? With the blockchain, you could do this, all right? Mathematical objects, think about it, created, bought, and sold, and traded on NFTs at the blockchain. I'm not talking Einstein's equations or Euler's or anyone else. I'm talking original ones. Ones that have never been published in papers. Not the Riemann oscillator, because that's published in this paper, but or at least in preprint. I'm talking just you as a mathematician. Go come up with a great idea, a beautiful identity, and go sell it. I'll buy it. If I like it, I'm going to go and put a bid on it. All right? And I'm going to come up some, and you like it, put a bid on it. So I want to start the discussion. This has never been done before, so this is brand new. Could be a crazy idea, but why not? What is more beautiful? They're selling art. They're even selling art based on mathematical equations. All right, and so math, everything in there is being digitized anyway. It's being reduced to mathematical objects. Why not just sell the mathematical objects directly? And what is the value in it? Well, it could depend. Is it proven or not? I would say do one that's not proven. If somebody proves it, the value goes up. Sell it again. I think this should be discussed. Everything else is being thought of how to put on there except mathematical objects themselves. Algorithms might be given value again. All right? So that's what I'm going to discuss, and I'm going to I think I'll open the discussion on this. It could be silly, but I'm already starting it. All right? I'm starting as an example, and I'm going to get into that in the next video. I want to show you what's going on. But as far as the proof of that, thank you. I hope it makes sense to you, but I want to move on to this other discussion because I think it's really the discussion of mathematics right now. Where is mathematics going? What is the value of these discoveries? I am a much bigger fan of research than I am proving. I love finding new properties of mathematics. I love creating beautiful objects like the Riemann oscillator. And I'd like to get into it. So please join me in the next discussion. And thank you. Have a great evening.